There's a planet 40 light-years from Earth that's worth more money than has ever existed in human history because it's made almost entirely of diamond. Not a diamond the size of a building, not even the size of a continent. A diamond twice the mass of Earth. For decades, astronomers dismissed this as theoretical fantasy. Carbon planets couldn't actually form this way, they said. The conditions were too extreme. Then we pointed our telescopes at a star called 55 Cancri and everything changed. So how does the universe accidentally create a jewel worth $26 nonillion? And what does it mean that we completely missed it? Here's what your astronomy textbook told you about planets. They form from disks of gas and dust. Rocky worlds like Earth end up with iron cores and silicate mantles. Gas giants balloon up from hydrogen and helium. Simple categories, clean rules. Think of it like a cosmic recipe. You start with certain ingredients, you get predictable results. For 50 years, that model worked beautifully. Every planet we found fit somewhere in the taxonomy. Then we discovered 55 Cancri. This world orbits so close to its star that a year lasts just 18 hours. Surface temperatures hit 2,400 degrees Celsius. But the weird part wasn't the heat. The weird part was its density. When astronomers calculated how much mass was crammed into this planet's volume, the numbers didn't work. Too light for rock, too heavy for gas. Something else entirely was going on inside. And then researchers at Yale proposed something nobody expected. What if this planet wasn't made of rock at all? What if it was made of carbon, compressed under unimaginable pressure into the largest diamond the universe has ever created? To understand how you make a diamond planet, you need to understand how stars die. In their final stages, stars fuse heavier and heavier elements. Carbon, oxygen, silicon. Usually oxygen dominates. That's why most rocky planets end up as silicates, basically fancy space glass. But some stars are different. They burn in ways that produce more carbon than oxygen. When these carbon-rich stars explode or shed their outer layers, they seed nearby space with enormous clouds of pure carbon dust. Now imagine a planet forming in that cloud. Instead of silicon and oxygen, it's built from carbon. Deep inside, where pressures reach millions of atmospheres, that carbon does what carbon does under extreme conditions. It crystallizes. Here's the number that breaks people's brains. The pressure at 55 Cancri-E's core is roughly 10 million times Earth's atmospheric pressure. That's not just enough to make diamond. That's enough to turn a third of the planet's entire mass into solid crystalline carbon. Wait, but wouldn't the heat melt it? This is where it gets fascinating. Diamond's melting point rises with pressure. At these depths, diamond is actually the stable form of carbon. The planet isn't just preserving a diamond. It's actively creating one, which leads to the part that most people never hear about. The real discovery isn't that one diamond planet exists. It's that diamond planets might be everywhere. Recent surveys suggest that 15 to 20% of stars in certain galactic regions are carbon-rich. That means trillions of potential carbon worlds across the Milky Way alone. Now extrapolate. If diamond planets are common, then the most valuable material in human civilization, the one we fight wars over, destroy ecosystems for, build entire economies around, is literally just floating around in space in quantities we can barely comprehend. The combined value of 55 Cancri-E's diamond, using Earth's market prices, would be $26 nonillion. That's a 26 with 30 zeros. More wealth than every economy in human history combined, multiplied by 1 billion. But here's what matters more than money. These carbon worlds represent an entirely different chemistry of planet formation. Different minerals, different geology, potentially different conditions for chemistry that leads toward life. We've spent decades assuming rocky planets look like Earth. What if half the rocky worlds out there have compositions we've never imagined? Diamond mantles, graphite surfaces, carbide cores, an entirely alien periodic table of planetary possibilities. So the real question is, does this change what we think is possible? Right now, the James Webb Space Telescope is actively studying 55 Cancri E in 2022. Webb detected the planet's thermal emissions for the first time. In 2023, researchers began analyzing its atmospheric composition. They're looking for carbon monoxide, carbon dioxide, and hydrogen cyanide, chemical signatures that would confirm a carbon-rich world. The results are expected within months, not years. Meanwhile, a team at the University of Arizona is running laboratory experiments to simulate diamond planet conditions. They're crushing carbon samples under millions of atmospheres to map exactly how these worlds behave. And here's what keeps them up at night. If Webb confirms 55 Cancri E's diamond composition, we have to rewrite planetary formation models from scratch. The textbooks will literally need new chapters. There's also the long game. Future missions like the Habitable Worlds Observatory, planned for the 2040s, could directly image carbon planets around nearby stars. We might see these diamond worlds as more than data points. We might see them as actual places. 40 light-years away, a world twice Earth-sized shimmers with crystalline carbon forged in the heart of a dying star. And now you understand why it exists. Not a cosmic accident, not a theoretical curiosity, a natural consequence of stellar chemistry we completely overlooked. The universe has been making diamonds for billions of years. We just never thought to look. So here's my question for you. If we eventually develop interstellar travel, should diamond planets be mined or preserved as natural wonders we never touch? Drop your answer below. Follow for more, we post every week.